Okay, so for number 2, we've got a magnetic field that's cylindrically shaped, and we've got a circular loop of wire within it. So that's this loop right here. And in this scenario, it tells us that the magnetic field is a function of time, and we can see that as time increases, the magnetic field increases. So what's the direction of the induced current? Well, if the magnetic field going into the page is increasing, we want to generate a magnetic field that is coming out of the page. So within the loop, magnetic flux, we want to counteract that increasing magnetic field in. So we're going to create a magnetic field coming out. And in order to have a magnetic field coming out using the right-hand grip rule, we have to have a current going counterclockwise. And as it curls, it comes out of the page on the inside. So this one would be counterclockwise. Derive an expression for the induced current in the loop. So for part B, we always know induced current is EMF over R, and EMF is equal to negative change in flux over change in time. Flux is dB dot A cosine theta, and we know that because the normal is parallel to the magnetic field, the cosine theta is just 1, so that cancels out. And we also know that between the area and the magnetic field is the one changing over time. So I'm going to put dB dt, and then EMF is equal to negative d dt of my function alpha plus beta t times my area. And the area of that circle is going to be pi r squared. And so when I take the derivative, I get negative beta pi r squared. Current is obviously, I'm going to add that here, EMF over R. So if I put this over R, I get the answer for current. And in this scenario, you can take the absolute value of it and just call it magnitude of b pi r squared over r. And then we talked about how the direction is counterclockwise, so that's where the negative comes from. So that is our equation for part B, or answer for part B. For part C, it says derive an expression for the induced electric field at any radius less than A. So if my R is within the magnetic field area, then I'm going to use Faraday's equation, which states that EMF is equal to the enclosed integral of the electric field dot ds, and that is then also equal to negative d flux over dt. Now, we already know that the EMF is going to give us not this whole equation, but at least this top part of this equation right here. So when we plug that in, then we can simplify things down. And I'm just going to take the absolute value of it. I've got the enclosed integral of E dot ds, and EMF is going to be equal to beta pi r squared. ds is going to be the circumference of this loop. It's the enclosed surface, so the length of that enclosed surface is going to be 2 pi r. And when we simplify things down, we get an electric field of, the pi's also cancel, beta r over 2. So this lets us know that a changing magnetic flux induces an EMF, which also induces an electric field. So this is part C. We're going to do the same thing for part D. So I'm going to do D in blue over here. This time we've got a loop that's greater than the magnetic field. And so we're still going to use the same equation. E dot ds is equal to EMF, or negative d flux over dt. And we already derived an equation for the flux, except for instead of r squared, the magnetic field is only as big as this circular area right here. So even though the radius of our the radius of our loop is larger, when we are looking at the total change in flux over change in time, we can only go up to a squared. So here it's going to still be beta pi, but it'll be beta pi a squared, and then that's equal to the enclosed integral, or instead of enclosed integral, we'll do e times that circumference of 2 pi r, some arbitrary radius out here r, and we can see that our function doesn't reduce quite as much, but we get an electric field of this magnitude right here. So remember, if we're looking at the change in flux over time, even if the loop is outside of the magnetic field, you only have as much magnetic field as is present, so that would be the full radius of a squared.